Hi everyone, time to graph some trig functions, section 4.5. We'll start with graphs of sine and cosine functions. How do we graph y equals sine of theta? Now, I'm going to use theta instead of x because I still want to think of theta as an angle. All right. Also, I'm going to consider theta in radian measure, which corresponds to real numbers, which is more standard. Remember, in our classic picture of the unit circle, we associate sine of theta with the y-coordinate of this intersection point between this terminal side and the unit circle. So to graph one fundamental cycle for y equals sine of theta, we're going to take a tour from theta equals 0 to theta equals 2 pi and track the behavior of the y-coordinate. I do that in this copy of my notes. And I'm going to use what is called the frame method, which my colleague Tom Teagarden and which the author Carl Smith have used. So here's what we're going to do. I'm going to draw a Kitkat bar where we have 3 horizontal line segments, evenly spaced, and 5 vertical line segments, evenly spaced, like this Kitkat candy bar. The theta axis, or sometimes the x-axis, will go through the middle, this middle line segment, and the y-axis, which I'll label as f of theta, the y-axis will go through the left edge over here. The origin, for right now I'm calling that the pivot. It's the pivotal point on this frame. The origin is at the left center of the graph. All right. I claim that a fundamental cycle for y equals sine of theta will look like this. I call this a good morning graph because you have a hill on the left. It's like we have a happy morning, and we have a valley later on. Okay, it's like a low-key night. So a good morning graph. So why is this the fundamental cycle for y equals sine of theta? Again, we're tracing the behavior of the y-coordinate. I'll shrink this. We're tracing the behavior of the y-coordinate along the unit circle. All right, so starting here, theta equals 0. When the angle theta equals 0, this flat angle, here's the corresponding intersection point. The y-coordinate here is 0. When theta is 0, theta is like x here on this graph. When theta is 0, y, or the sine value, is 0. So when theta is 0, y is 0, 0, 0 is on the graph. The origin, the pivotal point, is on the graph, the red graph here. As we increase the angle from 0 to pi over 2 radians, and we travel through quadrant 1, what's happening to the y-coordinate, the sine value? The sine value, the y-coordinate, is increasing from 0 up to 1. And the sine of pi over 2 is 1. Remember S-I-N? The sine of pi over 2 is 1. The sine value increases, and at pi over 2, the sine value is 1. By the way, notice that I'm writing the quadrantal angles on the bottom of this frame. 0, pi over 2, pi, 3 pi over 2, and 2 pi. I think it's nice to write these on the outside of the frame because I know that in trig, I always get annoyed when the graph runs into my coordinates, my numbers. So I like putting these numbers on the edges of the frame. And of course, that's fine. So again, the sine value goes from 0 up to 1. By the way, this part of the graph we're saying is concave down. Concave down. I'll shrink this a little bit. Concave down. Meaning that the graph is curving downward. And that's the case between 0 and pi, as it turns out. Okay, this piece of graph here, from here to here, the graph is curving downward. The graph is concave down, kind of like square root did, right? That guy. Concave down. And on graphs, you better get the concavity right. So we've gone from here up to here, which is a max point. We started at this middle pivotal point, and we're going up to this max point. It's one of the highest points on the graph. All right. Now, as we go from theta equals pi over 2 to theta equals pi, what's happening to the y-coordinate or the sine value? We start at 1 here, and it's decreasing. Y or sine is decreasing towards 0, and sine of pi is 0. Over here, the sine value is decreasing. Sine of pi is 0. And again, we have a middle point here. It is also an intercept, a theta intercept, but in general, I might want to call this a middle point or later an inflection point, because remember, we're going to move these graphs up and down later on. So it's not always going to be an intercept. Right now, though, for the fundamental cycle, y equals sine of theta, basic function, yes, this will be an intercept as well. All right, back here. The angle is changing from pi to 3 pi over 2. What's happening to the y-coordinate or sine value? It's going from y equals 0 down to y equals -1. The sine value is going down from 0 to -1. Sine of 3 pi over 2 is -1, and we're reaching a minimum point. This is one of the lowest points on the graph. And then finally, in quadrant 4, as theta goes from 3 pi over 2 up to 2 pi, the y-coordinate goes from -1 back up to 0. The sine value goes from -1 back up to 0. 2 pi is coterminal to 0, so it makes sense that sine of 2 pi equals sine of 0, which is 0. And we have completed a fundamental cycle for y equals sine of theta. The graph is concave down from theta equals 0 to pi. The graph is curving downward. However, the graph is concave up from pi to 2 pi. The graph is concave up over here. One thing that's convenient about the basic fundamental cycles for both sine and cosine is that the graph is concave down above this theta or x-axis. The graph is concave up below the theta or x-axis. That's true for cosine as well. All right, and notice here we have 5 key points on the graph, on these intersection points between these grid lines. We capture all these middle points. Right now they're intercepts. We capture this maximum point, and we capture this minimum point. Before, I referred to these middle points as inflection points, or IPs, which is kind of a calculus term. We mentioned these, remember, when we talked about logistic functions, where what we're hoping that coronavirus will do, where the graph is changing in curvature, right? So we have an IP here at these middle points, right? So an IP there, an IP over here at the middle point, an intercept right now, and an IP over here. And what is an inflection point? It's called an inflection point. You see this in calculus. What is an inflection point? It's a point where you have continuity, there are no breaks, and the concavity is changing. So here at this inflection point here at pi, the curve is going from concave down to concave up. That happens at all of these middle points. Right now, these are intercepts. All these intercepts here are also inflection points. In general, I'm going to call these points inflection points because, as I said, later on we're going to translate these graphs up and down, and they will no longer be intercepts, but they will still be inflection points. So this is an anatomy for the basic fundamental cycle for y equals sine of theta. Let's talk more about the features of this framing. Now, bear in mind, if you like your old method from Trig, Math 104, you don't have to use this framing that I'm doing here. However, you have to give me all the information that the framing method would have given me in a typical problem. Although you don't necessarily have to put in all these grid lines. I do think they're helpful, though. And as we'll see, it'll lead to some very nice, consistent, and systematic methods, which I think you might prefer to your Math 104 methods in Trig. So next, I will talk more about the framing. Okay. This is called 1 period. 2 pi is called 1 period, which we'll talk about later on. All right, but again, more about the frame, and then I'll talk more about the period and periodicity. Framing one cycle. Okay, so again, what were some key features? Drawing the Kitkat bar. So if you're doing a sine or a cosine function, you do the 3 horizontal line segments and the 5 vertical line segments, breaking up this candy bar. And you're going to get 5 key points. For a sine or cosine graph, you're going to get 5 key points that are intersection points for grid lines. In this case, we're getting this point, the max point, this point, an IP, the min point, and the IP over here. We're going to always break these things up into fourths. For a cycle, we're always going to break up a cycle into fourths. Okay, so the period is 2 pi, and we're going to break it up into pi over 2 increments. The left center point is this pivotal point. I'm going to call this point the pivot. It's the point that corresponds to the origin. Later on, it's the point that the origin will move to. And for sine and cosine graphs, the pivot will always be at the left center of the frame. For right now, it's at the origin. In fact, the pivot will be at the left center for all 6 trig functions, except for tangent. Tangent's going to be an exception. We're going to place the pivot at the center point for tangent. We'll see why. Again, it looks cleaner if we place coordinates on the bottom of the frame and to the left of the frame so that our graph isn't running into the numbers. That always used to annoy me as a student. Okay. Oh, and let's not forget, we need coordinate axes. It is not debatable that we need to label the axes. It's debatable what the order should be. So I might put the labels last. So theta here, y over here. I might put the labels last. But if you tend to forget, you might want to put these first. All right, but at some point you have to label the axes. The theta axis is our horizontal axis. Later on it'll be x. The vertical axis is the y-axis. You must label the coordinate axes. A lot of people forget that. It's debatable whether you do it later or earlier. Usually you do it earlier, but later on, when we start to really transform these things, it may turn out to be better to label the axes at the end, not at the beginning. But make sure not to forget them. All right. So we framed one cycle for y equals sine of theta. Next, we're going to talk about the period being 2 pi, periodicity, the overall graph for y equals sine of theta, and we'll move on from there next time.